Murugan, Kuppan, and Antoine Scalabre from the joint team CNRS and University of Bordeaux, study of interaction of porphyrin and cucurbituril with inorganic, organic nanohelices. So I don't know who will be the first.
I will be the first speaker of this talk. Thank you, Roberto. So how can I share, like, okay, can you all see my screen now?
Yes, now.
Okay, perfect. So hello, everyone. Me and Bara, we are both working on nanostructure, and we use them as template for chirality induction. So we split the talk into two, and I will speak first mostly on like general topic for this chirality induction. But first of all, of course, to get this, we need to form chiral nanostructures. So to do that, we start in our group from this 16, sorry, I will just put a laser, yeah, from this molecule, which we call 16-216 tartrate, and which we will represent like this. And if you put it in water, it will just self-assemble into double bilayers. And because of the chirality of this ion here, the tartrate contra ion, this double bilayer cannot stay flat. And so it will twist, and upon some time, you will form organic nanohelices in your medium. Of course, these helices, as I said, are organic, and they will evolve. They are not very stable. If you change, for example, pH, for example, temperature or something like that, the shape of your material will change. In order to stabilize it, we found one way, which is adding TOS in the medium, and then you will form a silica shell around the organic nanohelix. By doing so, you form these hybrid helices where the organic part is still inside, and you can see on the TEM picture that we preserve very well the supramolecular shape. What is interesting in our system is that the chirality only comes from this tartrate counter ion. So if you change the ion from, for example, D tartrate, which form left-handed helices, to L tartrate, then you change the handedness of the final helices from left-handed to right-handed helices. Also, another thing we can do is just by changing the aging time. As I said, you just disperse this in water and then you let it age. If you make various aging time, then after, for example, a few hours, you will get ribbons. But if you wait longer time, for a few days, you will have helical ribbons. And even if you wait even longer, after a week, the pitch will shrink, and then you will have tubes like this. What we are most interested in, of course, are twisted ribbon and helical ribbon, because the tubes are not chiral on a supramolecular way. So we have our silica helices. What can we use them from? And we find in several, within the few past years, we find a lot of ways to use them. For example, so as I said, they are chiral. So we can use them as template for assembly of nanoparticles. And I will come back to that a bit later. We can also use them for chiral photoluminescence and chiral optical properties in general. We can use them for asymmetric catalysis. Or since they have a periodic pattern, we can also use as bioactive nanostructures, for example, for the differentiation of stem cells. And they are strings-like, so they have very interesting mechanical property and can be used for sensors or this kind of application. Today, I will mainly focus on the chirality part, and so on the template property and also on the photoluminescence. So we have our hybrid helices, which I presented before. And if you zoom inside, it's a bit like this. So you have the silica wall and the organic inside. So you can use it like this, or you can also just put them in methanol and wash away the organic parts. And in this case, you get silica helices, and you can functionalize the surface with APTS, and you get a density of amine on the surface, which is around 1.1 per nanometer square. This is very easy to use after to graft, for example, gold nanoparticles on the surface, and you can observe on the CD measurement, you can observe a nice circular dichroism on the wavelength of the plasmon of the gold. So it means the gold nanoparticles are interacting together to give chiroptical property to your material. You can also go to smaller particles like clusters with POM clusters, and you also have induction of chiroptical property on the absorption of POM. But another challenge was to go to even smaller objects, and our idea was to go to organic chromophore. So we decided to graft very easily some chromophore which has carboxylic acid group. And to do so, we activate the carboxylic acid by ethyl chloroformate, which is very well known in the literature. And then you can attach them on the amine functionalized helices by amide bonding. So here I present you one example of this reaction with the pyrene derivative, and we can see the appearance of chiroptical property. And if you look at under TEM, you can see we preserve very well the shape of the helices. Also, by fluorescence, we can observe an excitable fluorescence, which attests the interaction between the molecules. And if you change the density to much higher value, so you graft more of the molecule on the surface, then you can increase by a lot the ratio of the exciter to the monomer. And here you have almost only excimeric fluorescence. And if you look on the chiroptical property, we find out that by increasing the ratio, the density of the molecule, then the G factor, so the dissymmetry factor of your material, increased tremendously thanks to this increase. Now, this is if you use your silica nanohelices to graft directly on the surface. But another way to use them is to, instead of removing the hybrid that I said before, to use directly hybrid helices. And if you exchange the inside ion, then you can have new chiral. Of course, inside here you have the tartrate molecule, which is chiral. To get rid of it, you can wash by potassium chloride, and then you can see, so this signal belongs to the tartrate, and after exchanging by potassium chloride, you don't have any signal left because the chloride don't absorb in the visible range. Actually, this is something which has been done with a lot of ion by somebody in our group. So you can exchange by bromide, by iodide, and you can observe chiroptical property, attesting that you have an interaction between the monoanion and the organic template inside the helix. And you can have chiroptical property. You can even go further, and you can use these helices as nanoreactor to form iodine or copper iode, and then you have also CD on the iodine, and CD and also CPL for the other molecule. Once again, we wanted to go to organic chromophore because it would allow us to use a wide range of wavelengths and so on. So if you put another pyrene derivative, for example, in the presence of the helices, then So for all these graphs, the concentration of pyrene is always the same, which is 60 micromolar. And if you increase the concentration of the helices inside, the absorption decrease, then increase, and at the same time, you have appearance of chiral properties. This is because of the conformational change when the pyrene inserts in the hybrid. After some adjustment to get the best condition, you can have very nice CD spectrum of this pyrene derivative, and also you can observe appearance of CPL for the material. So we could get a dissymmetry factor of 8⁻⁴, and for the CPR we have a GLUM of 1.3. So this was done for pyrene, but it can be done for many molecules. And for example, we did this also for porphyrin in order to be able maybe to attach some other molecule inside. And we observe the same kind of result with an increase of chiral property and a decrease of the absorption. And if you put iron in the same batch, you will, of course, observe first the iron chloride absorption, but after washing by water, the iron chloride leaves also the medium. So it means you cannot attach it. We think this is because once the porphyrin is inside of the hybrid, there is too much steric hindrance around it, and so it cannot attach something inside. But we will try several other molecules to do that. Of course, the chiral property don't change also upon addition of iron. So to sum up this part, and then I will let Bala continue. So we can make various systems from the same starting material. So we have twisted ribbon, we have helical ribbon and tubes. We can make them inorganic or hybrid. And we can, from the inorganic, we are able to use them as template for the aggregation of nanoparticle or clusters, but also even for smaller objects like molecules. And on the hybrid, we can use them to induce chirality on almost any anionic molecule. And we can even use it as a nanoreactor to have to induce chirality on species. So thank you for listening, and I will let Bala continue this talk.
Hello.
Yes, Bala, we can hear you.
So can we start? Okay, so let me start by sharing my screen. How does it work? Okay. Do you see the presentation?
No, at the moment, no.
Not yet.
I think you are okay.
Is it okay now? No?
Okay, now we can see the PowerPoint, so you can start you can put in the presentation mode.
Let me go to the first slide. It's taking some time. It's a bit slow. Yeah, is it okay?
It is not in the presentation mode. We can see just the PowerPoint.
Let me check again. How about now?
Not yet.
Yeah, sure. This is the first time I'm using the Microsoft Teams, so it's a bit tricky. Let me stop and restart my sharing. Sorry about that. You don't see it now, right?
No, we don't need nothing now. You remove the shading, so
because the network is a bit slow here, so it's taking its own time.
Antoine, if we want to save time, you can reply to the question
yes.
now.
You can
Yeah.
do that. Maybe.
So yeah, I can answer this small question. Can I just share my screen very fast for this answer? It will be very fast.
Okay. Yeah.
Okay. So I will just use this one because this is where I spoke about the G-lumen G factor. So the question was, can you comment on the difference between the dissymmetry factor in luminescence and absorption? So there is two reasons why we have this difference. The first reason is from the machine, because in the case of CPL machine, the sensitivity is not as high as the CD machine. G-luminescence, which is around 10⁻³ in this kind of case with very low fluorescence, is quite difficult to detect. And that's why we have, as you can see here, we have already quite a difference between the left-handed and right-handed helices. 0.3 is quite a lot. The second reason is because in the case of CD, you can observe here the absorption at 400 is not zero due to the scattering of our helices. This scattering will artificially decrease the dissymmetry factor that when we do the calculation, because it is considered in our calculation as absorption, whereas in reality it is not. So this is also a second reason why we have a smaller G factor in absorption than in emission. Sorry, Bala. Now you can.
Yeah. Can anyone tell me like what do you see? Like, do you see any of my
we don't
desktop?
See now we see some white, like a notepad or something like that.
How about the presentation?
Maybe you can try to share directly the screen rather than a window. You should be able to.
Because when I go to the share option, it's like
share directly screen. It is not elegant, but it should work.
You're not sharing. You see the presentation now, like if it's not in the presentation mode. Not yet?
No, not yet. No. Try to share screen number 1. You should have something like that.
Okay, let me check. Because there are also some network issues here, so it's a bit slow. Sorry about that. Oops. Is it still in the screen sharing mode?
Okay, now we see the web browser.
How about the presentation?
No.
Okay. Maybe I'll go to the screen number 1 as it said. I think that should help.
Screen 1.
Screen 1, yes.
Yes.
And now you can just run presentation from PowerPoint after that.
Okay.
Is it okay?
Yeah.
Perfect. Okay. Sorry about that. Okay, so let me start by first thanking the organizers for inviting me for this talk, and also the other previous people who have presented and make my work simple so that I don't have to touch upon the introduction of different topics. And also, I would also like to thank Antoine for this nice introduction about the supramolecular helices and the chiral nanostructures. So I'll be discussing about study of interaction of biotin urils with supramolecular helices, that is the chiral nanostructures. So how we can use supramolecular chiral nanostructures for chiral induction to biotin urils for detection of and sensing of chiral molecules. So with that, since Lucas has spoken widely about cucurbituril and also the other speakers have spoken about porphyrin, so I'll just give a very brief introduction and then go to the experimental part. So cucurbituril, as you know, it's a very interesting class of macrocycles, and apart from these macrocycles, they can form supramolecular vesicles, molecular machines, self-assembled structures, artificial ion channels, self-sorting systems, and most importantly, they are very good receptors for different kind of molecules and ions. And these can be classified as ions, gases, fluorophores, anti-cancer agents, peptides, neurotransmitters, and many other types of molecules and ions. So cucurbituril, since they have a very high hydrophobic cavity and also the concave hydrogen sticking outside, they can easily bind to anions and cations in general. So in this particular presentation, we'll be largely talking about hemicucurbitryls. As Lucas said, they have alternate carbonyl positions in the structure, so they cannot really bind to methions, but they're more specific towards anions. So with that, so in this work, we're more interested towards how we can combine chiral nanostructures and the macrocycle hemicucurbitryl. So both chiral nanostructures, the helical nanostructures and cucurbitryls, they belong to supramolecular chemistry, but they have their own individual roles to play. So as Antoine said, what are the importance and how these chiral nanostructures are formed and how do we prepare in ODA's book? So since he has largely spoken about it, I'll just quickly rush through the chiral nanostructures. So firstly, we prepare organic helix, which is prepared from Gemini tartrate, where the Gemini is the core micellar structure, which forms the fiber-like structures. And once you combine Gemini with tartrate, which is the chiral anions, these further form ribbons and chiral structures. And if you don't have this tartrate, it's just a it just forms achiral supramolecular structures. But the issue is these organic helix are not very stable, and if you want to do further chemistry on that, this is not a very good system to study if you just have the organic helix. So in order to make it more robust and stable, we cover this organic helix with silica coating, which is done by Solzil techniques using TOS as a chemical. So as you see in the model, you will have this organic helix, which has Gemini and tartrate. So tartrate forms the micellar structure, and then you have the Gemini forms the micellar structure, and then you have the tartrate anions. And the role of silica is it covers the entire organic helix between the silica layers. So this silica coating on the organic helix makes it highly stable and robust. So once you have this entire structure and you put the foreign molecule, these foreign molecules can penetrate through the porous silica membrane and take the chiral induction and the chiral transfer. And how does it happen? So in ODA's group, this can also be done by having tartrate as the anion and also the chloride. So the reason we choose chloride as the anion or different halide for the matter is because tartrate, as you know, is chiral, and if you try to study the chiral optical studies with a foreign molecule, the CD spectra will have the interference from the tartrate anions. To get rid of that, we have a more non-absorptive anion, which doesn't absorb in the CD region. So to do that, the tartrate anions are replaced by chloride, and then you have the organic helix, silica-coated organic helix with a non-CD anions. Not only that, compared to tartrate, chloride ions are much more easier to replace if you have a foreign molecule. So this is about the organic helix, and interestingly, the organic helix can also be further converted to inorganic helix by removing the organic organic template, which is buried inside the silica, which is buried within the silica walls. So we will see how we will use the silica helix having tartrate as the anion, chloride as the anion, and also how the inorganic helix itself is more useful for some important studies and experiments. So this is about the organic helix in Ottaw's group, and then since the other portion of the talk is cucurbituril, so it was we must be very thankful to Professor Rina Aur's group from Tallinn Institute of Technology, who gave us the cucurbituril molecules and also the conjugate molecules to carry out this entire study. So we have been given 3 molecules, which is the biotin ureal as such, and then we also have the biotin ureal monoconjugate with the porphyrin attached to it. So we will see how we have used these 2 molecules. So to start with, we have started a study with biotin ureal molecules in combining with circummolecular helices, and then we had some results, and in order to confirm those results, we had to go for the monoconjugate molecules. So we will see those study one by one. But before going, why do we, if you clearly notice, these are cucurbitals which are chiral. So why do we need chiral? So the whole idea about this study is to finally use this entire material for sensing of chiral molecules, chiral pollutants, and things like that. So in order to do that, you need to have a chiral template, and you need to have a chiral substrate for detection of chiral molecules. So if you just say, for example, if you start with achiral cucurbituril, and then you have an enantiomeric or enantiomeric mix of chiral pollutants or chiral molecules for that matter, it's difficult to sense. They won't, the achiral cucurbituril cannot sense between the 2-handed enantiomers. But if you have the chiral cucurbitils as we are going to study in our system, and if you have enantiomers, the one set of cucurbituril molecule will have more preference towards a particular enantiomer in a recipe mixture than compared to the other one. But so this itself is useful because we know that cucurbituril macrocycle is very specific macrocycle and can bound to different kinds of molecules, say it be chiral and achiral. But to further enhance its chiral induction properties and also make it make the entire system more selective, we thought of putting the chiral cucurbituril molecules into an chiral nanostructure template. So when we do that, the entire chiral sensitivity of the cucurbituril gets enhanced by doing that. So how do we do that? So if you have, say, you have a chiral nanostructures and you have achiral cucurbituril, for example, it won't have a it will have a selectivity because of the entire chiral nanostructure template function, but not because of the cucurbituril. But if you combine the chiral properties of the cucurbituril and also the chiral nanostructures, the chiral properties of both the system combined together gets enhanced, and all gets enhanced. And if you take one, for example, the helices can be left-handed and right-handed. Say you start with a right-handed helices, as in this case, and you let it interact with a chiral cucurbituril molecule, and then try to sense a recipe mixture. So since the system is already, I would like to represent, maybe I can quickly go back and show how the molecules are represented. So the biotin ureal molecules without the porphyrin conjugates will be represented as this for convenience, and the monoconjugate will be represented in this form. And we also have the monoconjugates with zinc and without zinc. So initially we started experimental work by combining the chiral nanostructures, the helices, with the cucurbituril. And if you see the chiral optical studies, The blue line here indicates only the CD properties, CD features of the cucurbitryl alone, and you see that there's hardly any signal and it's more towards the noise. But the moment you combine the cucurbitryl molecule with the helix, with the both left-handed and right-handed helix, you see that there's an inflection and there's an enhancement in the CD, but it's not much. Like the people who are studying larger and chiral properties would know that the jump is not much, but there's a significant difference between the cucurbitryl molecule alone and once it's combined with the supramolecular helices. So, and when we further discuss these results with Professor Reena, it was suggested that this could probably be the incorporation of chloride anions from the chloride-based helices with the hydrophobic cavity of the cucurbitryl. So, and may not be because of the chiral induction from the helices to the cucurbitryl. So in order to confirm that the cucurbitryl is actually penetrating through the silica wall and getting intercalated between the helices and it's undergoing a chiral induction properties, we thought of having a fluorophore, because if you know that cucurbitryl molecule is not a very strong chromophore and its absorption falls in a very short UV range. So it becomes very difficult to analyze and study. So we thought of having a strong chromophore attached to the cucurbitryl and then see if the chiral induction properties of the foreign molecule attached to the cucurbitryl actually gives us some story about the incorporation. So to do that, we had this molecule where the cucurbitryl was attached in a monoconjugate fashion to porphyrin. So the benefit is that cucurbitryl molecule is already chiral, and there's a chiral induction from the cucurbitryl to the porphyrin. And when you just record the CD properties of the cucurbitryl this monoconjugate molecule, it shows a clear CD signal, as if you see the blue line here. So that was very useful for us because it shows intense CD signal and also in a region between 400 to 500, which doesn't interfere with the helices region in the UV region. So this is quite useful, and then we went ahead with the studies. So when we combine the supramolecular helices with these monoconjugate molecules, and interestingly we saw that initially the left-handed helices showed CD signal which was very much similar to the monoconjugate. But interestingly, when you combine these monoconjugate molecules with the right-handed helices, it shows opposite CD signal, which was very interesting. It also confirms the incorporation of the monoconjugate within the helices. Say if you don't have this opposite-handed CD properties, and if it's same as the D, then it would suggest that the CD features which is coming in this region without the opposite-handedness is mainly because of the intrinsic CD features of the monoconjugate and not because of the chiral induction from the helices to the monoconjugate. But the very opposite CD signal which comes from the when you put the monoconjugate in the other handed helices, it shows it's a clear indication that there is a chiral induction from the helices to the cucurbituril and then to the porphyrin. So this was this gave a strong evidence to us, and which led a positive direction for us to use the entire cucurbituril supramolecular helices, that is a chiral nanostructure helices, to use for the studies. So we have been speaking about the chiral optical properties, but how do these monoconjugate molecules actually interact with the supramolecular helices? So as you see, when I show these helices, so it has the outer silica layer, and then the Gemini micellar molecules arranged in a bilayer fashion, and then you have these chloride anions which are replaced from the tartrate. So we start with tartrate, replace with chloride, and then we carry out these studies. So because chloride it's not a chromophoric molecule, and if you record the CD, there won't be any CD signal. But the moment you put the monoconjugate signal, these monoconjugates having strong carboxylic acid groups on the cucurbituril, they once they penetrate, they try to replace the chloride anions which is present within the silica walls, which is present inside the silica walls. So these slowly start replacing the chloride anions in the supramolecular helices, and then it takes the chiral induction or asymmetric transfer from the porphyrin from the helices to the cucurbituril. So the moment you have this transfer of when you have this exchange of chloride by the cucurbituril molecules, you will have this chiral induction happening, and one will see the CD signal. So how does it happen? So, as I said, the monoconjugate molecule itself showed an intense CD signal. So that happens, and it shows in a region which is not intrinsic for the cucurbituril, but which is for the porphyrin. So when the monoconjugate has a chiral induction from the cucurbituril to the porphyrin, and once you put inside these supramolecular helices, the chiral nanostructures, there is a chiral induction from the helices to the cucurbituril, and then there is a chiral induction to the porphyrin finally. So it can be called an asymmetric transfer in a cascade fashion. What is interesting is, even though the main interaction happening inside the helices is between the cucurbituril and the Gemini ions, and porphyrin is more in a remote fashion. By the final CD induction, the CD induction happens at the porphyrin. So the entire system is quite useful for sensing of chiral molecules, and how the chromophoric properties of the porphyrin can be used as an evidence to show that these huge cucurbituril molecules can actually be put inside the supramolecular helices for large number of sensing studies. Now the question arises is, you have this the silica helices is a combination of silica wall and inside the organic helices. So the question is, do the cucurbituril monoconjugate does interact with the silica wall? Like they can be chiral induction where the cucurbituril doesn't actually penetrate within the silica helices, but is actually attached, non-covalently attached on the surface of the silica wall, and it still has a chiral induction happening. To prove that the cucurbituril monoconjugate is actually getting inside the supramolecular helices, and then it's showing the chiral induction properties, we did some studies. So the experiment was planned in this way. We started with the chiral nanostructure having chloride as the anion, and it's well established in Noda's group that once you treat this helices, the hybrid helices with hot methanol, you can easily retain this silica helical structure and remove the organic content which is present within the silica walls, and then finally you just have the inorganic silica helices. So this is how it is. So you'll have the organic content, the pink color material which is between silica walls, and upon treatment with hot methanol, you can retain the silica structure and remove the organic. So the whole idea was, if we can prepare this inorganic structure and then combine this with the monoconjugate and see if we still show the CD properties. So before going to that, what we did was we already have this we have this hybrid helices, which has the both silica and the organic part, and it has the monoconjugate within inside the helices. So we thought, let's try to subject this material to methanol washing, and if we can more or less remove the organic content and see if the monoconjugate is still attached to this silica wall. So when we did that, as you see in the absorption, we did the chiral optical studies before at this stage, that is before washing and after washing. So in terms of the absorbance, you see that when you do the washing, and since if the monoconjugate is part of the organic, it should get washed away when you wash with methanol, and that's what it happens, and the absorption drops significantly, and you just have a small amount of the monoconjugate which might be still present because of say not complete washing. And this can be further confirmed from the CD properties. When you see that, obviously before washing, you will have these equal and opposite CD signals for both the handed helices with the monoconjugate. And after washing, the CD features are still intact with the opposite handedness. So this indicates that even though most of the organic content with the monoconjugate gets washed away, there is still a small amount of content which is present, and it shows CD signal. And this can only happen if the monoconjugate with the organic if the monoconjugate can actually penetrate inside the silica through the silica wall and interact with the organic content inside. And a more details and direct evidence can be obtained from this study, where you take the supramolecular helices and then subject to methanol washing and convert into inorganic helices, and then try to combine this with the monoconjugate and see if there's any kind of induction happening. So if at this stage, if there is any CD signal coming from this system, it's an indication that the monoconjugate is actually interacting with the silica wall and with only the silica nanostructure, and not with the organic helix which is present within the silica wall. So interestingly, the black and red are for the initial, the usual standardized CD properties for the monoconjugate with the hybrid helices. But after washing and once you prepare the inorganic helices and try to react the monoconjugate, both the D and the L silica nanostructure, they show the same CD signal without any opposite handedness, and which is also similar to the CD properties of just the biotin-urea. So this confirms that the monoconjugate doesn't actually react with the silica wall, but it reacts with the organic helices which is present between the silica walls. So with this, we can clearly state that the monoconjugate with the cucurbituril can easily be incorporated in the hybrid helices and can be used for further studies as a strong chiral nanostructure template with a microcycle. So since this chiral optical studies were well established in terms of absorption properties, we were also interested to see if the system it shows chiral optical properties in terms of the luminescence characteristics. To do that, we did CPL study for this well stabilized cucurbituril monoconjugate with the supramolecular helices, and but unfortunately we didn't see any CD features. So if you see that the blue line is for the monoconjugate alone, which has low fluorescence intensity and also doesn't show any CPL features. And same is the case for the D and the L form, which doesn't show opposite handedness. And also in terms of the signal, the CPL signal it's still too low. So we are still working on it and see if the CPL features can be obtained and if the system can be tuned to have a good CPL properties. And interestingly, we could see some sort of difference between the fluorescence intensity for the two handed helices, and this has to be further looked into. Will be looked in very carefully to see if there is any selectivity between the left hand and the right-handed helices with the monoconjugate, and that can be done by studying different lifetime studies and also detailed steady state fluorescence studies. So with that, I would like to summarize the talk. So we have started with studying the interaction of cucurbituril with the supramolecular helices, and to gain further evidence, we combined the monoconjugate and looked into the chiral optical properties. And once you know that the CD features are there's chiral interaction happening, we did some confirmation study to show that the monoconjugate actually gets incorporated within the organic helices and not on the silica wall, and that was done to confirm with some inorganic helices and hybrid helices system. And lastly, we have also done some preliminary studies on studying the CPL studies and also the fluorescence studies for these monoconjugate supramolecular helix. So this, and so it is still in the initial stage, and studies are still being carried out, and Antoine is taking it further for more detail and thorough optimized system. Where once it's optimized and stabilized, this can be, we will see how this can be used for sensing and detection of chiral pollutant, which is the main interest of the entire project. So thank you all for the attention, and I would like to take some questions. Thank you.
Okay, thank you, Bala, for the talk. I think
thank you.
We are quite late and
yes. And still sorry about the initial glitch over the screen sharing.
We can